Assalamu alaikum warahmatullah. This is Akramuzzaman Onto from Elevare and I am your IGCSE Physics instructor. Today I will be solving the IGCSE Physics May June 2025 regional paper, which is basically paper 1, and I will be walking you through every question step by step and showing you exactly how to get full marks and avoid common mistakes. The solution video is basically divided into two parts, part 1 and part 2, and the part 1 consists of questions 1 to 6. So without any further ado, let's jump right into question 1. All right. So the question 1 is about a truck traveling along a horizontal road. The diagram shows a truck traveling along a horizontal road. As we can see that the truck is traveling along a horizontal road and there are two horizontal forces being levied. One is a driving force, another one is a total resistive force. Okay. The first question is, the diagram shows the horizontal forces acting on the truck. Give the resultant horizontal force acting on the truck. Okay, so what does resultant horizontal force mean? Resultant horizontal force means the vector sum of the horizontal forces acting on the truck. Vector sum of the horizontal forces acting on the truck. Vector sum of the horizontal forces acting on the truck. So when we say vector sum, what do we actually mean? Vector sum actually means that when we are adding the forces, we will have to consider the direction as well. Let's say we have considered the direction of the driving force to be positive. So the opposite direction must be negative. So if I consider this direction, or if I consider the right direction to be positive, the left direction must be negative. So by considering these things, I can write the driving force as positive 16 kilonewton, and I can write the total resistive force as negative 16 kilonewton. Now when I add these forces together, considering the directions, I'm going to get the resultant horizontal force. So positive 16 kilonewton plus negative 16 kilonewton, that actually gives us 0 kilonewton. So the resultant horizontal force is basically 0. Alright, so we have solved the first part of the first question. The driver of the truck has to stop because the tree has fallen on the road. The thinking distance of the driver is 7 meters. The braking distance of the truck is 20 meters. Calculate the stopping distance of the truck. In order to calculate the stopping distance, we will have to use the formula for calculating stopping distance, which is stopping distance equivalent to thinking distance plus braking distance. So the thinking distance is equivalent to 7 meters. Braking distance equals to 20 meters. If I add them together, I get 27 meters. So the total stopping distance would be equivalent to 27 meters. Okay. Give two factors that would affect the braking distance of the truck. So there are several factors that affect the braking distance of the truck. We just have to write any two out of them. But I would obviously suggest to memorize all of these factors, because sometimes the question might ask you to write three factors. So if you just memorize two and in your exam the question asks you to write three, you won't be able to write the last factor. So it is best to memorize all the factors that affect the braking distance of the truck. So the braking distance is basically affected by the speed of the truck, the mass or weight of the truck, condition of the tires, condition of the road, condition of the brakes. So these are the possible factors that affect the braking distance of the truck. There are other factors as well, but I will be only writing the common ones, and memorizing them will help you achieve full marks in these type of questions. I will be writing all the factors, but you just have to write any two for this question. So the first one being the speed of the truck, speed of truck. Second one is basically mass or weight of truck, mass or weight of truck. The third one is condition of brakes, condition of brakes. Then condition of tires, and obviously condition of roads. If the road is wet, then obviously there would be very little friction between the tires and the road, and hence the braking distance would be more. Condition of road. All right, so you just have to write any two factors out of all these 5 factors. Let's move to the last part of this question, The last part states which of these factors would decrease a driver's thinking distance. Okay, so there are four options, and out of these four options, we just have to cross out the correct one. The road is dry rather than wet. So this factor actually affects the braking distance and not the thinking distance. We know that the condition of the road affects the braking distance. If the road is dry rather than wet, then obviously the braking distance would be decreased because there will be greater friction between the tires and the road. So this factor affects the braking distance and not the thinking distance. It has no relation with the thinking distance. The truck has old, worn tires rather than new tires. So this factor also affects the braking distance and not the thinking distance. This one also affects the braking distance and not the thinking distance. If the truck has old, worn tires, then obviously there will be very little friction between the tires and the road, and the braking distance would increase. The driver is tired. Now, the tiredness of the driver directly affects the thinking distance. But if the driver is tired, the thinking distance is not going to be decreased. Rather, the thinking distance is going to be increased. Why? Because if the driver is tired, the reaction time is going to increase. If the reaction time increases, the driver is going to take long to react, and hence the thinking distance would be large. So this factor obviously affects thinking distance. This one obviously affects thinking distance, but it actually increases the thinking distance rather than decreasing it. All right. So we are left with only option D. The truck is traveling at a lower speed. Now we know that speed affects the braking distance. Speed also affects the thinking distance. Speed also affects the thinking distance. Speed is basically a factor that affects both thinking distance and braking distance. So if the truck is traveling at a lower speed, our thinking distance would be smaller. And if it is moving at a higher speed, the thinking distance would be larger. All right, so the answer to this question would be option D. Yeah, so that was it. That's the solution for question number 1. I hope you have understood and have got no doubts in this question. Strong bar magnets, and the bar magnets are actually held very close to each other. All right. There is a uniform magnetic field between the poles of the bar magnets. So between the poles of the bar magnets, there is a uniform magnetic field. Complete diagram 1 by drawing magnetic field lines to show the uniform magnetic field. You should label the poles of the bar magnets. First of all, uniform magnetic field exists between opposite poles. That means if I consider this pole to be north, this must be south. Or if I consider this as south, this must be north. So let's say we considered the left bar magnet to be north and this one to be south. Okay, now we will have to draw the magnetic field lines. In a uniform magnetic field, the magnetic field lines are straight and the magnetic field lines are evenly spaced. We will have to remember these two criteria. One is the magnetic field lines are straight and the magnetic field lines are evenly spaced. So if I draw evenly spaced horizontal lines in between these two bar magnets, that would be the magnetic field lines, and which will actually show the uniform magnetic field. So let me try drawing horizontal lines in between these two bar magnets. So that's the first horizontal line, and we will have to just copy them, and we will have to place these lines at equal distances. Make sure you place these lines at equal distances. The lines must be drawn at equal distances because in a uniform magnetic field, the magnetic field lines are evenly spaced. The magnetic field lines are evenly spaced. Another thing that is, you just have to draw a minimum of 3 or 4 magnetic lines. You don't have to fill up the entire space. But what I usually do is that I usually fill up the entire space because it kind of looks cool and it kind of actually looks more sophisticated. But you have the opportunity to draw only 3 or 4. and you will be actually getting full marks if you draw 3 or 4. All right, so I have actually filled up the entire space. Now we will have to uh, put the direction of the magnetic field. So the direction of the magnetic field is always away from north and towards the south. Always away from north towards the south. So the direction of the magnetic field would be from the left to the right, from the left to the right. So make sure you place arrowheads in all of the magnetic field lines. All right. All right, so here I have drawn the uniform magnetic field that is present in between these two poles of two strong bar magnets. The first mark could be awarded due to writing north and south pole. Doesn't matter the orientation, you can actually write this one as south, this one as north. In that case, you will have to reverse the direction of the magnetic fields. The second mark is the drawing of these horizontal straight lines, and you will have to draw a minimum of 3 horizontal lines. Then the third mark is the equal spacing of these horizontal lines. That means if these lines are placed evenly, only then you will be securing the third mark. And the fourth mark is basically the direction of the magnetic field prior to the orientation of the poles. All right, so that was the first part of the second question. Let's move to the second part. The diagram 2 shows a strong magnet attracting an iron block. So this is actually our strong magnet, and it is attracted to an iron block. Okay, the iron block becomes magnetized when it is in the magnetic field of the strong magnet, right? Because iron is basically a magnetic material. Label the magnetic poles on the magnetized iron block in diagram 2. So the iron block is basically attracted by the strong magnet. When the iron block is attracted by the strong magnet, the iron block becomes a magnet temporarily. So since the strong magnet is attracting the iron block, this one should be a north pole and this one should be a south pole, because opposite poles attract. The question has clearly stated that the magnet is attracting the iron block. So if the magnet is attracting the iron block, so the south pole is basically attached to the iron block. It can only happen if this end of the iron block is north, because we know that opposite poles attract. If this one was south, then the strong magnet wouldn't have attracted the iron block. All right, so that was the solution for B1. Then B2. A student takes a strong magnet away from the iron block. The student suggests they can permanently use the iron block to attract small pieces of iron. Explain whether the student's suggestion is correct. The student's suggestion is wrong. Why? Because as soon as a strong magnet is removed from the iron block, the iron will actually lose its magnetism. Iron will lose its magnetism. Iron is a magnetically soft material. Magnetically soft material only becomes temporary magnets when they are around a magnetic field. But once a magnetic field is removed, at that time, the magnetically soft material loses magnetism as well. So the student's suggestion is wrong, because iron will lose its magnetism, since iron is a magnetically soft material. Only magnetically hard materials can be permanently magnetized. So the answer would be something like this. The student's suggestion is wrong. The student's suggestion is wrong. Then iron would lose its magnetism. Iron would lose its magnetism as soon as the magnet is removed. As soon as the magnet is removed. Why? You have to explain, so you will have to put a reason. Because iron is a magnetically soft material. Because iron is a magnetically soft material. All right, so we are done with question 2 as well. I hope you have understood all the parts of question 2. All right. All right. So question 3 is about electrical circuits. This question is about electrical circuits. The table shows the circuit symbols for some electrical components. So the table consists of some circuit symbols of few electrical components. Complete the table by placing ticks to show whether each component can visibly indicate the presence of current in a circuit. Complete the table by placing ticks to show whether each component can visibly indicate the presence of current in a circuit. Visibly indicate the presence of current in a circuit. All right. So if you actually think what the question has asked us to do, we will have to place ticks corresponding to those electrical components that can visibly indicate the presence of current in a circuit. All right. So first of all, you will have to think about resistors. If you think about resistors, resistors cannot visibly indicate the presence of a current in a circuit. Why? Because resistors can either increase or decrease the current. It can only alter the current, but it can't visibly indicate the presence of current in a circuit. So among all these electrical components, you will have to find the resistors present. All types of resistance will actually does the same work, that is altering the current in the circuit, but they don't actually visibly indicate the presence of current in the circuit. So you find all the different types of resistors present in this list, and excluding those ones, the remaining ones should be our answer. Another thing, the marks for this question is 3. So this actually indicates that there are 3 options, or there are 3 answers to this particular question. So first of all, find all the different types of resistors, and excluding those ones, the remaining ones would be our answer. Okay, so the first one is basically a variable resistor. Variable resistor. So resistor actually does not indicate the presence of current in a circuit. So this won't be our answer. We won't be placing any tick on this one. Okay, now this is basically LED, which we call light emitting diode, LED, and this indicates the presence of a current in a circuit. If the current flows in the allowed direction, or if it flows in the direction opposite to the restricted direction, only then the LED will glow. In other words, this can actually indicate the presence of current in a circuit visibly. So this would be our correct answer. Then this is bulb or lamp, and this will obviously indicate the presence of current in a circuit. This is actually a thermistor. This is basically a thermistor, and a thermistor does not indicate the presence of current in a circuit. Since it is a resistor, it will only alter the current in the circuit, but won't show whether there is current in the circuit or not. Then this one is basically light dependent resistor, or LDR, and this won't be our correct answer as well. The final one being the ammeter, and the ammeter obviously indicates the presence of current in a circuit visibly, because if you see a reading in the ammeter, you actually understand that there is current in the circuit. If you see no reading, then obviously there is no current in the circuit. So from this question, we actually understood that any kind of resistor does not involve in indicating the presence of a current in the circuit, because the resistor can only alter the resistance, and by doing that, what it actually does is that it either increases or decreases the current, but it doesn't show the presence of current. All right, so that was the answer to the first part of question 3. Okay, question 3b shows an electrical circuit containing a cell and component X. So this one is the cell, and this is actually component X. The graph shows how the resistance of component X varies with temperature. So we can actually see how the resistance of component X varies with temperature. So as we can see that this graph is basically a fraction graph, right? This graph is basically a fraction graph, which is basically the graph associated to inversely proportional relationship. Give the name of component X. As we can see that the graph, the shape of the graph is associated with an inversely proportional relationship. So from here we can deduce that resistance is inversely proportional to temperature. Only when resistance is inversely proportional to temperature, only when you understand that resistance is inversely proportional to temperature, you can actually deduce from this particular fact that this graph would be of a thermistor. This graph would be obviously of a thermistor, because in a thermistor, the resistance is inversely proportional to temperature. So if I actually write the relationship, resistance is inversely proportional to the temperature, and if I write the equation, that will be equivalent to K by T. K is a constant. So a fraction graph actually looks like this. A fraction graph looks like this. And if there is a relationship which is directly proportional, let's say there are two variables which are directly proportional to each other. Let's say y is directly proportional to x, then there would be a straight line passing through the origin. The shape of the graph would be a straight line passing through the origin. And if two variables are inversely related to each other, then the graph would look like this. The graph would look like this. The graph would have a shape like this, because fraction graphs have a shape similar to this one. So we know that in thermistor, the resistance is inversely proportional to temperature. And so from the graph, we can deduce that the name of the component would be thermistor. Another way you can deduce that these two variables are inversely related, which is you take two sets of values from the graph and you multiply them, and you will see that there would be a constant value. If you take two sets of values from the graph, and when you multiply these two values, you see that there is basically a constant value. All right. So that will also indicate that these two variables are inversely proportional. All right. So we are done with this one. Let's move ahead. Use a graph, determine the resistance of component X when its temperature is 50 degrees Celsius. So we will have to use a graph to determine the resistance of component X when its temperature is 50 degrees Celsius. So let's find 50 degrees Celsius on our x-axis. So that's 20, 30, 40. So this is going to be 50. All right. So this is going to be 50. We just have to find the corresponding y value of 50. So that's pretty easy. You can do that by drawing lines, and that will help you to find your answer more precisely. So if I read this value from the y-axis, if this one's 100, this has to be 50. So 10, 20, 30, 40, 50. This one is 50. So this one has to be 60, 70, 80. All right, so the resistance of component X when the temperature is 50 degrees Celsius is 80 ohms. Okay. The cell in diagram 1 has a voltage of 9 volts. This cell has basically a voltage of 9 volts. Okay. Calculate the current in component X when its temperature is 50. They also have provided you the formula. Voltage is equals to current into resistance. You will have to calculate the current. You are provided with the voltage, and also you know the resistance at 50 degrees Celsius. So you use the values of voltage and resistance and make the current subject in this particular equation, and then you will be able to calculate the value of current. Voltage is equivalent to 9 volt. Current is equivalent to I, the value which we have to calculate, and the resistance is equivalent to 80. You just make I the subject. You make I the subject. That gives you 9 over 80, and the value for current would be hence 0.11 ampere. The answer to this question should be written in two significant figures, because the data was provided in two significant figures. As you can see, 9 volt is in two significant figures, 50 is in two significant figures. So the value for current must be in two significant figures as well. Okay. Now, next question. The circuit in diagram 1 is modified by adding a second identical component X in series with the other components. So the circuit in diagram 1 is modified by adding a second identical component X in series with the other components. So in the circuit we had component X, and now the question states that the circuit has been modified by adding another resistor in series with the circuit, and that's also basically X. That's also X because they have said that they have added an identical component X. So this one's a thermistor, hence this one is also a thermistor. And these two thermistors are identical because that's what the question has told us. So both of these thermistors are identical. In other words, if this thermistor follows a resistance against temperature graph like this, then this one also follows the same graph. This one also follows the same graph since both of these thermistors are identical. All right. The temperatures of the first component X and the second component X are reduced to 26 degrees Celsius. So the temperature was initially 50. Now the temperatures are reduced to 26 degrees Celsius. So the temperature of X is now 26. The temperature of this thermistor is also 26, right? Okay. The question is, explain how the resistance of the circuit is affected by these changes. The question is, explain how the resistance of the circuit is affected by these changes. Okay, now let's see how the resistance of the circuit will be affected. Previously, the resistance was 80 ohms, right? Previously, the resistance was 80 ohms. Previously, the resistance was 80 ohms. So previously there was only one component though, but now the circuit is modified to have two components, two identical components, and both of them are thermistors. Both of them are identical thermistors. So where the temperature was 50 degrees Celsius, the resistance of this component was 80 ohms, or in other words, the resistance of the circuit was 80 ohms. But now there are two thermistors, two identical thermistors, both of them are at the same temperature. So as I have mentioned before, both of them will follow the same resistance against temperature graph. So if I find the resistance at 26 degrees Celsius, let's just find the resistance at 26 degrees Celsius. So this one's 30. So this should be 22, 24, and this one's 26. So let's find the corresponding Y value of 26. So this is 100 and this one should be 150. 10, 20, 30, 40, 50 and 160. In other words, the resistance of X is basically 160 ohms when the temperature is 26 degrees Celsius. Now, if the resistance of X is 160 ohms at 26 degrees Celsius, this one would be obviously 160 ohms as well. Why? Because both of the thermistors are identical. So both of them are actually following the same resistance against temperature graph. If I get the resistance of X as 160 ohms at 26 degrees Celsius, then obviously the resistance of this one should be 160 ohms at 26 degrees Celsius as well. So in series circuit, the resistance needs to be added. The total resistance in the circuit in a series circuit is equivalent to R1 plus R2, right? This one, let's say this one's R1 and this one, let's say this is R2. And we also know that R1 is equivalent to R2 in this case. So adding them together, we get the total resistance as 160 plus 160, 320 ohms. So previously it was 80 ohms, but now it's 320 ohms, which means the resistance of the circuit has increased. All right, so the answer to this question carries 4 marks. So we will have to be very careful while writing the answer to this question. First of all, we will have to identify that the resistance of both of these thermistors would be 160 ohms. We will have to mention the fact that since both of these thermistors are identical, their resistances would be identical as well. And we will also have to include the idea that when two components are present in series or added in series or connected in series, they will have more resistance. So yeah, that would be our answer. And finally, we will also have to write that the total resistance of the circuit is 320 ohms. So let me write the answer for you. The first point would be the resistances of the resistance of both thermistors would be 160 ohms. The resistance of both thermistors would be 160 ohms since they are identical. Alright, that's the first point. The second point would be that when two components are connected in series, when two components are connected in series, the resistance increases. The resistance in the circuit increases. Resistance in the circuit increases. All right. The third point would be since both of the resistors have the same resistance, the total resistance of the circuit is doubled. Finally, we will have to write that hence the total resistance equals 320 ohms. Alright, so that would be the 4 points for the 4 marks of this question. I hope you have understood this question. This question was pretty simple, and I hope you have actually understood all the parts of question 3. Alright, so we are done with question 3. Alright, so question 4 is basically an experimental question. Question 4 is actually an experimental question. A student does an experiment to investigate energy transfer by conduction. So the student is going to conduct an experiment, and in this particular experiment, the student is going to investigate energy transfer by conduction. Alright. The student plans to use the piece of apparatus shown in the photograph. So if you check the photograph, the student plans to use this apparatus. The apparatus consists of 4 metal bars, and the 4 metal bars are made of different types of metals, and one end of the bar is basically immersed into hot water. There are temperature sensitive strips attached to these metal bars. Alright. The apparatus has 4 bars made from different metals. When the apparatus is placed in hot water, energy is transferred from the bottom of the bar to the top of the bar. So when the apparatus is placed in hot water, as you can see that one end of the bars are actually immersed into hot water. So these bars conduct heat from the hot water, and the heat energy is transferred from the bottom to the top. Okay. The temperature sensitive strip on each bar changes color as the temperature of the bar changes. So as the temperature of the bar increases, the color of the temperature sensitive strip changes. So as the heat energy is transferred from the bottom to the top, as the heat rises all the way to the top of the metal bar, the color of the temperature sensitive strip changes. Okay. Now the time taken for the color change to reach the top of the bar can be used to compare how effective each metal is at transferring energy by conduction. So the time required for the top temperature sensitive strip to change color can actually tell us how effective each metal is at transferring heat energy by conduction, right? So the first question is, give 3 control variables in the student's investigation. So in this particular investigation, the student should maintain the length of the metal bars. The student should maintain the length of the metal bars, right? The student should also maintain the thickness of the metal bars. Student should also maintain the width of the metal bars, and the student should also place the metal bars at each height, at the same height inside the hot water. In other words, the metal bars must be immersed into the same depth. The metal bars must be immersed into the same depth inside the hot water. Alright, so these are actually the control variables, and also the initial temperature of each metal bar must be the same. The initial temperature for each metal bar should also be the same. So let me write all the control variables. You just have to write 3 out of all the variables that I will be writing. All bars of equal length, that will be shorter. Bars of equal length, then bars of equal thickness. Third variable can be bars of equal width, and bars should be at the same depth inside water. At the same depth inside water. Finally, same initial temperature. Same initial temperature of each bar. Same initial temperature of each bar. Okay, so that was the answer for A1. Let's move ahead. A2. So the student has this equipment. The student has got a beaker. The student has a hot water. The student has stop clock, and the student has clamp and clamp stand. Design a method the student could use to compare the effectiveness of the metals at transferring energy by conduction. You may draw a diagram to help your answer. So first, let's just discuss how are we going to carry out the particular experiment. In order to answer this type of questions, where you will be asked to design a method or to design an investigation, and you will be provided what type of investigation should be carried. First of all, just discuss the things that you have and how those apparatus can be used to particularly make a setup in order to carry out this investigation. And also you will have to think how the investigation would be carried out and what is going to happen during this entire experiment. So what we can actually do is that we will be provided with the apparatus. We will be provided with the apparatus. I mean, I'm talking about this one. We'll be using this one. The student will be using this particular apparatus. So one of the equipments is this one. Then we will have a beaker. So we'll have to immerse the apparatus into the beaker. The beaker will obviously contain hot water, and the particular apparatus, I mean this one, would be attached with a clamp and a clamp stand. This one would be attached with a clamp and a clamp stand. And the clamp and the clamp stand is actually used to hold this one, because this actually ensures that all the metal bars are at the same depth inside the hot water. So this is how you can actually set up all these apparatuses, and this setup can be used in order to carry out the student's investigation. So what the student is going to do is that the student is going to record the time taken for the top temperature sensitive strip to change color in case of each metal bar. The student is going to record the time required for the top temperature sensitive strip to change color for each metal bar. And then the student is going to compare the time taken. So that's how the student can actually use to compare the effectiveness of each of these metal bars in conducting heat, right? So this is the setup. First of all, the student needs to immerse the apparatus into the hot water and start the stop clock immediately. Then the student needs to wait for the top temperature sensitive strip to change color in case of all the metal bars. And then the student should record all these values in a table. The student should record the values in a tabular form. The student is going to record the time required for each corresponding type of metal. The student can actually then compare these values, and that will enable the student to compare the effectiveness of the metals and transferring energy by conduction. So first of all, we will write support the apparatus using clamp and clamp stand. So what we will be doing is that we will be supporting the apparatus using clamp and clamp stand. This is basically the apparatus we are talking about. They didn't provide a particular name for this one, so that's why we are referring to it as apparatus. So we will support the apparatus using the clamp and clamp stand, and this actually ensures that all the metal bars are at the same depth inside the hot water. Okay, then we will place the apparatus into the hot water and start the timer or stop clock immediately. Place the apparatus into hot water and start the timer immediately. Then the student is going to record the top temperature sensitive strip to change color for each metal bar. Student is going to record the time required for the top temperature sensitive strip to change color for each metal bar. Third point would be record the time required for the top temperature sensitive strip to change color. So record the time required for the top temperature sensitive strip to change color for each metal bar. Now after that, in order to make the results more reliable, the student needs to repeat. Using the same apparatus. So the student has to allow the apparatus to cool. After the apparatus has cooled, then the student is going to repeat the entire experiment once more and will calculate multiple values of time for each metal bar. And after that, the student is going to calculate an average value. So the fourth point would be allow the apparatus to cool. Allow the apparatus to cool so that the apparatus reaches to the initial temperature again, which is basically the room temperature. Then we will be recording multiple values of time. Record multiple values of time by repeating the experiment for each metal bar. Record multiple values of time by repeating the experiment for each metal bar. Then finally, you can write calculate a mean value. Calculate a mean value for each time recorded. Calculate a mean value for time for each metal bar. For each metal bar. So the metal bar which actually takes the shortest period of time for its top temperature sensitive strip to change color would be the most effective to transfer heat by conduction, right? All right. So that's actually the answer for question 5. That's the answer for question 5. That's the setup. This one's the setup for this particular experiment, and this is the method. I hope you have actually understood this one. Okay, moving ahead, the table shows the results of the student's investigation. So this is basically the results of the student's investigation. The student has actually determined time for the color change to occur in seconds. So for aluminum, it's 29 seconds. That means for aluminum, the time required for the top temperature sensitive strip to change color is basically 29. For brass, the corresponding time is 64. For copper, the corresponding time is 22. And for steel, it's 115. Plot a bar chart of the student's results. So we have been asked to plot a bar chart of the student's results. I've actually plotted the bar chart once. I can show that to you. All right, so this is actually the bar chart for this question. This is how the bar chart looks like. Notice how I have placed the grid. The y-axis would be obviously the time taken for color change in seconds, because that's the dependent variable, and the independent variable is obviously metal. Now in this question, you can actually use key. You can use key for aluminum, key for brass, key for copper, and key for steel. Or you can actually write their names corresponding to each bar at the bottom. And make sure when you draw a bar chart, you will have to make sure that you cover 50% of the entire graph. I have covered more than 50, but a minimum of 50% must be covered. A minimum of 50% must be covered. All right. I hope you have understood how to draw this one. Okay. Moving ahead, we have got another question for question 4, which is deduce which metal is the most effective at transferring energy by conduction. So the most effective metal at transferring energy by conduction would be the one which actually requires the least amount of time, or the shortest time, for its top temperature sensitive strip to change color. So if you look at these values, 29, 64, 22, 115, among all these values, 22 is basically the least. In other words, copper is basically the most effective at transferring energy by conduction, because it requires the shortest time for its top temperature sensitive strip to change color. This actually refers that in order to transfer heat energy from the bottom to the top of copper requires the shortest period of time, which means copper is basically most effective at transferring energy by conduction, because it requires the shortest amount of time. So the answer would be copper. Why? Because the time taken to change color is shortest. The time taken to change color is the shortest. And the least effective should be steel, because the time required to change color is basically the longest. So yeah, that's actually the solution for question number 4. I hope you face no problems with this question and have understood each and every part of this question. Now, question number 5 is about radioactivity. The photograph shows a cloud chamber used to observe alpha radiation produced by a radioactive source. The radioactive source is inside the cloud chamber as shown in the photograph. So here is our radioactive source. here is basically a glass viewing window. So this is just a glass, and you can actually observe alpha radiation produced inside the cloud chamber by the radioactive source. Okay. Describe the structure of an alpha particle. So alpha particle is basically a helium nucleus that contains 2 protons and 2 neutrons. So we will be writing alpha particle is a helium nucleus that contains 2 protons and 2 neutrons. That contains 2 protons and 2 neutrons. Okay. Next question is basically solving a nuclear equation, completing a nuclear equation. The source used in the cloud chamber contains the isotope radium-226. The incomplete nuclear equation shows the decay of radium-226 into an isotope of radon. Complete the nuclear equation by writing the correct numbers in the boxes. So we have been told that radium-226 decays into radon by emitting an alpha particle. So we know that alpha particle has got 2 neutrons and 2 protons. So the number at the bottom represents atomic number or the number of protons. We know that alpha has got 2 protons, we're going to write 2 over here. And the number at the top represents mass number, which is equivalent to the number of protons plus the number of neutrons. We know that alpha has got 2 protons and 2 neutrons. So 2 plus 2 is equivalent to 4. Its mass number is going to be 4. Now, we have to know another particular fact in order to solve nuclear equation, that is the mass number at the left hand side must equal the mass number at the right hand side. The proton number at the left hand side must equal the number of protons on the right hand side. So number of protons has matched at both sides of this particular nuclear equation, but in order to balance the mass number, we will have to write 222 over here, because 222 plus 4 equals 226. So that's how we actually complete nuclear equation. We will have to remember that the number of protons on both sides of the nuclear equation is equal, and mass number at both sides of the nuclear equation is also equal. Okay. The tracks in the cloud chamber can be seen through the glass viewing window. So the tracks that are produced inside the cloud chamber can be seen through the glass viewing window. Explain why the radioactive source is not a hazard to the person viewing the cloud chamber. So the particular reason for why the radioactive source is not hazard, because the radioactive source emits alpha particles, and alpha particles are not dangerous when they are outside the body, because their penetration power or penetration ability is weak. They have got a very poor penetrating ability, and alpha particles are not dangerous outside the body. They are only dangerous when they are inside the body, when they are inhaled, and when they get inside the body, only then they are very, very harmful, because they are because they are high ionizing particles. So the alpha particle is basically outside the body. The first reason would be that alpha particle is outside the body. The alpha particle is outside the body. And the second point would be, since it has got a poor penetrating ability, since it has a poor penetrating ability, it has a poor penetrating ability, it can't actually penetrate the glass or the cloud chamber. Since it has a poor penetrating ability, it can't penetrate the glass. It can't penetrate the cloud chamber or the glass. All right. So we are done with question C as well. The last question of this one is basically D. When radiation is emitted from the source, a white line is produced in the cloud chamber. The white line is basically known as a track. Okay, so these white lines are basically track. These white lines are called tracks, and these white lines can be seen inside the cloud chamber. The diagram shows the tracks produced by the radiation from the source. So these white lines are actually produced by the radiation from the source. These white lines are called tracks. The diameter of the cloud chamber is also shown. The diameter of the cloud chamber is basically 10 centimeter. This is the radioactive source, and the alpha particle radiation is represented by these white lines known as tracks. Question is, explain the properties of alpha radiation that can be deduced from the length of the tracks. So in this type of question, where you are provided with a diagram and where the question is from the diagram, you will have to write the answer completely based on the diagram that you are provided. You will have to write the answer completely based on the diagram that you are provided. You cannot actually write any other points from outside. You will have to write points and make reasons completely from the diagram that you are provided. So you will have to explain the properties of alpha radiation based on what you can see. Okay, now first things first, as you can see that all of these tracks are of equal length, approximately equal length. All of these tracks are approximately equal length. So another thing that you can observe, that these tracks are much smaller than the diameter of the cloud chamber. The diameter of the cloud chamber is 10, whereas the length of these tracks are much smaller. All right. So the idea that the tracks are of equal lengths indicates that all particles have the same kinetic energy. The idea that all the tracks are of equal length or identical length, this actually provides us the idea that all these alpha particles have the same kinetic energy. Then we can also observe that these tracks are much shorter compared to the diameter of the cloud chamber, and this indicates that the alpha particles are highly ionizing or poorly penetrating, because since they are highly ionizing, they are actually absorbed by the particles in between their path, and since they are poorly penetrating, they can't actually penetrate the medium in which they are in, and hence they are absorbed very quickly, or they are absorbed within short ranges. So we actually make two observations. We can only make two observations from this diagram, and we write only two explanations for these two observations. All right. So the first one was, all the tracks are approximately of equal length. All the tracks are approximately of equal length, and this reinforces the idea that this shows that all alpha particles have the same kinetic energy. All alpha particles have the same kinetic energy, have the same kinetic energy. The second observation that we can actually make from this diagram is that the tracks are short, and this actually reinforces to the property of alpha particles that they are highly ionizing or poorly penetrating. So this shows that alpha particles are highly ionizing. Since they are highly ionizing, they are easily absorbed by matter, and so they are absorbed by matter before they travel long distances or long ranges. So these were the observations that could be deduced from the length of the tracks. One was the tracks were of equal length, and other one was that the tracks were short. And the corresponding properties that could be understood from these observations were written. One was that all the alpha particles have same kinetic energy, and the other one was that the alpha particles are highly ionizing. So having equal length actually reinforces the idea of having same kinetic energy, because the tracks represent alpha particles and the tracks ended at equal points. So this shows that initially they had the same kinetic energy or identical kinetic energy, and that's why they got stopped at equal points, which means they had equal or identical speeds before. So yeah, that was actually the discussion of question 5 and the answer to the last part of question 5. I hope you have understood this one and have no problems with this one. All right. Now we will be solving the last question of the first part of the solution video of this paper, which is basically question number 6. The question number 6 is about a rocket being launched at Cape Canaveral in the United States of America. The photograph shows a rocket being launched at Cape Canaveral in the United States of America. All right. The table gives some information about the motion of the rocket during the first 5 seconds of its launch. So the information is about the rocket in the first 5 seconds of its launch. First 5 seconds of its launch. So the initial velocity is basically 0. Acceleration is 13. Time taken is basically 5 seconds. Calculate the final velocity of the rocket after 5 seconds. Calculate the final velocity of the rocket after 5 seconds. Calculate the final velocity of the rocket after 5 seconds. Assume that the acceleration remains constant during this time. So in order to calculate the final velocity, we will be using the formula. A is equals to v minus u by t. So I know the acceleration, I know the initial velocity, I also know the time. I just have to calculate the final velocity. So if I make the final velocity the subject, I will be getting v is equals to u plus at. So now I will just be substituting the values of u, a and t to calculate the value of v. The value of u is 0 and the value of a is 13. The value for time is 5. Hence, the value for final velocity would be 65 meters per second. Final velocity would be 65. Okay, so after 5 seconds of the rocket's motion, the velocity of the rocket would be 65 meters per second if it continues to accelerate at 13 meters per second squared. Calculate the distance the rocket travels during the 5 seconds. Assume that the acceleration remains constant during this time. So we will have to calculate the distance traveled during this 5 seconds. So in order to calculate the distance traveled during the 5 seconds, look what do we have. We have got the final velocity, we know the initial velocity, we know the acceleration, and we also know the time. So we can actually use the formula v squared is equals to u squared plus 2as in order to calculate the distance traveled during this 5 seconds. S is basically the distance traveled, so we just have to find the value for s, and if we find the value for s, we will get the distance traveled during this 5 seconds. So technically we don't have to know the time, we don't have to know the value for time in order to calculate the distance, but we have to know the value for final velocity. So we will place the value for final velocity, which is 65 squared, initial velocity is 0 squared plus 2 times acceleration is equivalent to 13 and times s. So s would be equivalent to 65 squared over 13 times 2 is equivalent to 26. That gives us 160 meters. So answer to this question would be 160. Okay. Now question number C, where we will have to sketch a velocity time graph and distance time graph. Okay. Sketch a velocity time graph and distance time graph showing how the motion of the rocket changes during the first 5 seconds of its launch. You do not need to include values on the axis. So we just have to sketch a velocity time graph and distance time graph during this 5 seconds of the rocket's motion, and we don't have to place any kind of values on the axis. So as we know that the rocket is moving at a constant acceleration, they have told us that the acceleration remains constant. So if the acceleration remains constant, we know that the gradient for the velocity time graph is basically acceleration. So if acceleration is constant, this means that the gradient for the velocity time graph is also constant. So a graph where the gradient is constant is basically a straight line, and this would be a straight line passing through the origin. And since the rocket is accelerating, which means the gradient is positive, so the gradient of the graph should be positive as well. So the graph should look something like this. Since the gradient is constant, the shape of the graph is basically a straight line. As the gradient is positive, the line is moving upwards, and it will be a straight line passing through the origin. So this would be the shape of your velocity time graph. In case of the distance time graph, the gradient of the distance time graph is basically velocity or speed. In this case, speed. So in this case, speed and velocity actually means the same thing. So the gradient of the distance time graph can be speed or velocity. As you can see that the velocity during this 5 seconds is not constant. The velocity is varying. The velocity is basically increasing, or in other words, the speed is basically increasing during these 5 seconds. So since the speed is increasing, the gradient of the distance time graph is also increasing. So the distance time graph would be a curve, but the curve would be of increasing gradient. The shape of the graph would be such that the graph represents that the gradient is increasing, because as you can see that the velocity is increasing as the time progresses. So the distance time graph cannot be a straight line because the gradient isn't constant. The gradient is gradually increasing as the speed or velocity is increasing. So the shape of the graph would look something like this. If I draw roughly, this is the distance time graph for the rocket. As you can see that the gradient of the graph is gradually increasing. If you draw a tangent at this point, and if you draw a tangent at this point, the tangent at this point is much steeper than the tangent at this point, which shows that the speed or velocity is greater here than here. And gradually the graph is getting steeper because the gradient or the velocity is gradually increasing. So this should be the graph for distance time, and this should be the graph for velocity time. Alright, so I hope you have understood the sketching of velocity time and distance time graphs, and with that we have completed the first part of this solution video. I hope you have understood each and every question. I have tried to explain each and every part of all these 6 questions. If you face any difficulties still, drop them down on the comment section below, and let me know whether you have understood the explanation of all these questions or not. Until then, bye bye.